talking about the problem of routing some special kind of nets. Namely, we will be talking about two such nets, one is clock and the other is the power. Now, this clock and power nets are very important in terms of the overall performance of a system. So, the issue of routing these nets are taken up separately, because there are some stringent requirement for these nets which need to be satisfied. For a clock net, there are some issues like clock skew which need to be addressed, and for the power and ground nets, there are the issues like the current carrying capacity, they need to be addressed, and also the parasitics, the impedance. So, we start with talking about clock routing. So, what are the issues involved and what are the different techniques which people have proposed. Now, in clock routing, in terms of the problem formulation, just I am repeating. So, we need special algorithms to route these nets. Well, we are talking about power, we shall clock, we shall subsequently be talking about the power nets as well. They are important and they need specialized algorithms because there are some strict specifications which are often different as compared to conventional signal nets. So, for this reason, for these kind of nets, people have developed special purpose routers so as to meet their individual requirements. Now, the development of these special purpose routers will also simplify the general router, because if you want to incorporate all the constraints in the single router, then the router algorithm may become quite complex. Typically, these two nets are routed separately. This is done either manually or through a semi-automated process. Normally, clock and ground, they are not entirely left to the automated router to complete an interconnect. Particularly for high performance design, an accurate clock routing tool is essential. So, talking about clock routing, well, as you know, clock synchronization is very important in VLSI circuits, because in a typical VLSI circuits which work in a synchronous fashion, so all the data transfer and operations in the data path, they are carried out in synchronism with the clock, they are synchronized with respect to the clock. So, if we can have a design with a fast clock, well, obviously the performance of the circuit will improve. So, our aim is to have a design with the fastest possible clock. Of course, there will be some hard constraint which will be coming in with respect to the delays of the combinational network which are there in the circuit, because you cannot run the clock at a frequency higher than that. Now, there is another issue which need to be addressed, because in a typical chip, the clock signal is typically generated external to the chip. So, either you supply a clock input from an external oscillator, or there is an oscillator which is located somewhere near the periphery of the chip. You connect a crystal externally, so the oscillator generates the clock signal from one corner of the chip and then it gets distributed. So, the idea is that the clock signal is coming from one corner of the chip, and typically it has to go to every possible places in the chip, because depending on the requirements of the different functional blocks which you have spread out. So, externally you have this clock pin, this is what I call, and each functional unit inside the chip which needs the clock, they will have to be connected to the clock pin. So, we have something called a clock net. Now, a clock net is also very similar to a conventional net in the sense that it connects several pins which are located at specific coordinates. But the main difference in the clock net is that the cardinality of this net is much higher as compared to conventional nets. Typically, it is not uncommon that a clock net will have to connect to thousands of pins. Okay. So, this is one issue which need to be addressed specifically, and in order that we may clock the circuit at the fastest possible rate, well, in the ideal situation we desire that the clock should arrive at the different functional units all at the same time. if there is a variable delay between the, you can say, in the different paths, suppose the clock is generated here, this is the source of the clock, this can be that external pin I am talking about, and as it is getting distributed, if the delays of the different paths are different, delta 1, delta 2, delta 3, then the clock edges will be reaching the functional units at slightly staggered in the axis of time. So, if the clock edges come staggered in the axis of time, this is what is called clock skew. Clock skew means due to variable delay, the clock edges all do not reach the different functional units at the same time, there is a variation. So, if there is a clock skew, what is the requirement is that you will have to estimate the worst case clock skew, the delay variation which is possible, and effective clock cycle time will have to be enhanced by that. So, your effective clock rate will become slower, your clock frequency will go down, because if you try to run the circuit at the maximum possible clock rate, there you are ignoring clock skew, you are assuming that all edges come at the same time. But if you say that, well, there is a variation of 1 nanosecond between the two edges, then you must add 1 nanosecond to a clock time period in order to take care of that skew. So, just you must give or provide for sufficient time so that the skew may exist and still the different functional blocks may compute their outputs correctly, they are given sufficient time to do so. So, if there is a skew, the clock will have to be slowed down in order to take care of that. So, from the designer's point of view, it is essential to have a clock distribution network where the clock skew is minimized. So, the main purpose of the clock network is to minimize the clock skew. Okay. Now, talking about the various clocking schemes, well, these things are fairly simple things, you already know this, that you can have a number of different options. You can have single phase clocking with either latches or flip flops, or you can have multi phase clocking, typically 2 phase. Now, if you have single phase clocking with latches, the scenario is something like this. There is a, suppose it is a D latch, D input, this is the output. Well, although we are calling it a clock, this works more like an enable. This latch opens when the clock is high. The input data will get latched and the output changes continuously. Now, as soon as the clock goes down, the latch closes and the output becomes stable. Latches are sensitive to level, not to the edges of the clock. Normally, in conventional designs, we do not go for latches like this, we rather go for flip flops where clock edges trigger the data transfer. They are easier to design, but latch based design also has its merits, in particular for very high performance circuit, for very high speed designs where you need some asynchronous sub circuits in our overall design. There these latch based circuits work better, because when you have edge based clock circuits, you are tied by that clock period, you cannot do anything faster than the clock period. But if you have this kind of latch based circuit, whenever or the as long as the clock is high, so the any change in the input will propagate to the output. Okay. But as I said, most of the conventional designs today, they work with flip flops, where the flip flops is triggered either by the leading edge or the falling edge of the clock. So, only at the edges the output will change state in response to the applied input. Actually, for greater flexibility and highest speed of operation also, most of the complex circuits use multi-phase clocks. Well, a 2-phase clocking is very typical, because most of the flip flops which we use in circuits have a master slave kind of a structure, which are often clocked with 2 different non overlapping clocks. Well, one can be generated by inverting the other, or this clock and clock bar can be 2 separate clock inputs which we generate. these are non-overlapping, these are not necessarily complement of one another, they are in general non-overlapping. One may be like this and the other may be like this. Okay, so I am not going into details of this, all these things you know. So, that whether irrespective of whether it is single phase or two phase clocking, the issue of clock skew remains equally important. So, if we can minimize clock skew, we can run this circuit at a higher speed. Okay, fine. Now, as the rule of thumb, most of the practical systems, well, 10% is a rule of thumb which you can say that this is the maximum clock skew I can tolerate. Well, if my ideal clock frequency is f, well, I can allow the clock frequency to go down by 10%, but not more than that. Well, if I see that it is going down by more than 10%, then my clock distribution network has some problem. So, in order to achieve this, we need a good layout of the clock network, which is called the clock distribution strategy. Of course, in conventional system this is important, and in high performance circuit this is an absolute mandatory requirement, because in case of high performance circuit, a bad clock distribution circuit can destroy the very purpose of your design. Okay. So, clock distribution circuit is very important. Now, here another thing I am mentioning, that since the clock distribution is so important and we want to have minimum skew in the distribution, it is often the case that the entire clock network is routed on a single layer, because as you switch from one layer to the other through the via connection, there are some additional parasitic effects which will incur additional resistive and capacitive loads. So, there can be some kind of variation in those loads, and the delay can again go on changing over different paths. So, you prefer to lay out the entire clock net in a planar fashion in a single layer. Okay. Fine. Now, typically we use clock buffering because, as I said, the number of destinations of the clock network can be many, it can be of the order of thousands. So, a single, you can say, source, a normal source cannot feed the clock net to 1000 destinations. We need some good buffering mechanism to provide the required drive, current drive typically. And this clock signal is global in nature, global in the sense that it is a signal which is common to the whole chip. So, it should go to all corners of the chip. Since it has to go to all corners of the chip, clock lines are typically very long, and as you have long wires, they will have larger capacitances and also larger impedances, resistance. So, RC delay of these clock nets will play a big factor. So, we will have to take care of the RC delay to find out, that means how much delay is encountered in the different, you can say, segments of the clock network. Well, it does not matter that much if a clock signal is delayed with respect to what is entering the chip and what you are sending to a function unit, but it will suffice if I can ensure that the delays of all the paths are approximately equal. Maybe I am applying it to the input of the chip at time t1, they are all reaching the function units at a time t2. t2 minus t1 may be large, but I do not care about that. I am happy if the clock reaches all the functional units equally delayed in time. Well, equally delayed means there is no skew. Okay, fine. And one issue is that RC delay you cannot reduce by simply making the wires wider, because if you make the wires wider, R will decrease, but C will increase. So, by making the wires thinner or thicker, you really cannot change RC delay appreciably. To reduce the RC delay, buffers are used. This is one point I also mentioned earlier, because in a interconnecting line connecting 2 points, well, there are distributed resistive and capacitive loads. So, you can treat this as a something similar to a transmission line, and it can be shown that the total delay in that line is proportional to the square of the distance. Okay. So, if you can break the line into smaller segments and insert buffers in between, then the total delay can decrease. What I am saying is that rather than using a single buffer, suppose there is a buffer, an inverter acting as a buffer, distributing it over a long distance to a destination here, if you use a relatively smaller buffer, break this line up into several segments and then distribute it, then there are two things. Since these buffers are small, their delays will be less. Since these line segments are small, some of their delays will be much less than the delay of the overall line, because the delay is proportional to the square of the distance. So, if I break it up in this way, the delay in this partitioned buffer network will be less in general as compared to a network without any distributed buffers. Okay. Well, for the timing I am assuming that this is the generator and this is the destination. I will come to skew. Yes, this will also take care of skew. So, buffers need to be used. Buffers serve two purposes. One is of course the reduction of delay, as I had mentioned, and second is that it will also preserve the clock waveform, because as it traverses over a distance, the rising edge and falling edge gets degraded. So, if you use buffers in between, the edges get again sharp. So, you again regenerate the clock signal. So, signal degradation is also controlled. And in fact, these buffers alone may occupy as much as 5% of the total chip area. So, this is not something which you should underestimate. For distributing the clock network is a big network I told you, you must insert buffer in crucial places all throughout, and the total area occupied by buffer can be pretty large. Now, there are two broad approaches to clock buffering. I am talking about these. The first approach is something which uses a centralized buffer. So, here you have a central buffer which has a very high current driving capacity. Typically, when you need a buffer with a very high current driving capacity, instead of designing it as a single buffer, normally you design it as a cascade of several buffers with the size increasing slowly. That is how I have shown here. This is a central buffer which is near the source of the clock. This is the source. Now, once you have generated this clock signal with sufficient driving strength through this buffer, you can distribute it in some kind of a tree network. Now, you must lay out this tree network in a suitable way, so that the distance of each segments of the tree up to the leaves are equal from this point. This is one approach. You use a big buffer and a passive interconnection network. But of course, one problem with the passive interconnection network is that if these lines are pretty long, then again the signal degradation will occur. Well, if you are careful with the total length of these lines, well, skew can be controlled, but signal degradation is there. If there is a signal degradation, the rise time and fall time degrades significantly, then also you have to keep some tolerance in the clock period. Okay. So, something similar to clock skew also occurs. So, the speed falls. Yes.
So, what's the point in taking three buffers of increasing size, because the current drive for the chips is ultimately being supplied only by the last buffer?
No, this is that, see, this is a standard method of designing, means high current driving capability. Suppose you have a requirement to drive a very high capacity load. Ultimately, in terms of VLSI chip, These are all typically CMOS gates which need to be driven. So, from this point you can look at it as driving a very high capacitive load. Now, it can be shown mathematically very easily that instead of using a very big buffer to provide the required current driving capacity, big buffer means the resistance value is small. So, RC time constant is within limit. So, if you progressively increase the sizes of the buffers and connect them in cascade, each buffer is f is bigger than the previous buffer by a factor of f. Then it can be proved that the total current driving capability and the total means RC time delay gets controlled to a great extent. There is a formula, there is a way to calculate how many buffers you need in that cascade and what is the sizing. This is a standard VLSI technique. I am not going into detail in this class, but if you are interested to know about this, you can look at any standard book on VLSI design. You will get there design of current driving buffers, why these are connected in cascade with increasing sizes. Okay, fine. So, here we use a single buffer, big buffer, that is why we need this kind of a cascade, a very high current drive capability. But the other approach says that, well, we distribute buffer in the branches of the clock tree, do not use a single buffer. Now, here it says that you use all identical buffer. There will be many buffers distributed all throughout the clock tree and all of them will be identical in terms of the sizes, right. And if we use identical buffers and if the tree is symmetrical with respect to the length of the segments up to the leaf nodes, then the delays introduced in all the branches will be equal. Well, this demands some kind of a regular layout of the clock tree. This we shall be looking at very shortly, that how the clock tree layout can be made regular. But for the timing, let us see that how this buffer distribution can be done over the clock tree. Well, this again you can conceptually look at it like this. These are the buffers. These are all distributed on the different segments of the tree and so on, and from the clock source you distribute them like this. Now, the buffers are called identical because, for example, in this example I have shown the fan out of each of the buffers is 4 in the first stage as well as in the second stage, as well as it will be in the third stage. So, the final buffer also will be driving 4 clock pins. So, if you can ensure a symmetrical network like this, then ultimately the different clock pins which will be at the leaf level, they will be encountering equal delays from the source, right.
Sir, all these subsequent buffers from one stage to another will be equidistant from the.
They will have to be equidistant. Yes, see, this is a conceptual diagram I have drawn, but now we shall see exactly in terms of the geometrical coordinates that how this can be laid out. This is just a conceptual picture. I am saying that all segments of the trees are equal in length, then the delays will be equal. So, now we will be looking at the actual clock routing algorithms which will talk about how to lay out these wires on the surface of the silicon. So, clock routing algorithms, of course, the main issue here is to minimize the skew. So, the clock routing algorithms that have been proposed, they talk about distributing the clock signal in such a way that the interconnecting paths from the source to the final destination or the leaf nodes in the tree, they are equal in length. So, we have to ensure somehow that from the source of the clock to the destinations where you are connecting finally to the functional pins, they are all equal. Well, length is not the correct term, I should say they are equal in delay. the delay from that point to all those pins should be equal. But as the first approximation, we can say length and delay are proportional. So, we can also consider length as a measure. Now, there are a number of algorithms which have been proposed. Well, some are general, which can be applied to general designs. Some are special purpose, which are not applicable to general designs, but applicable to special cases only. So, we will be quickly looking at some of these algorithms: H tree, X tree, method of means and medians, weighted center, zero clock skew. These are some of the methods which have been proposed. Now, this H tree based algorithm is a very interesting and you can say this is a way in which you can lay out the clock net in a very regular way. See, first we will show how the clock net is distributed. The buffers we can introduce later. So, the H tree algorithm is simple in concept. The tree can be constructed recursively. The tree is constructed recursively at every stage of the iteration. You have a segment of the tree which looks like an H, that is why it is called H tree based algorithm. Now, you assume that you have an H like this and your clock is being fed to the middle of this H. This is the source of the clock, and these are the 4 points where you are finally producing the clock. These are the destinations, you can say. In the first level of iteration, these are the 4 clock destinations. Now, if you lay this out in a regular way, we will see in terms of the grid lines 1, 2, 3, 4, 1, 2, 3, 4. This is laid out as a 4 by 4 grid. So, now you see with respect to the source, each of the destinations are at a distance of 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. So, all the 4 corners of the H, they are at the same distance from the source. This is the first level of iteration. Now, the second level of iteration says, well, now we have been successful in generating the clock in these 4 points. Now, from these 4 points, these are the 4 points. Now, you treat these 4 points as the, well, in fact, not this, actually these points are this. So, these will be treated as the source of the clock signal for the next level of iteration. So, the next level of iteration you have 4 smaller H's in these 4 corners. One H here where this is the source, there is another H, this is the source, another H, this is the source, another H, this is the source. So, now from 4 we now have 16 destinations. If you count from the master source, the distance to each of the destinations are still the same, because from here the distance to these were same, and from these points to the 4 new points the distance will again be the same. But of course, the resolution of the grid we are increasing at every step of the iteration. We are increasing by 4 times. So, the next level of iteration it will go from 16 to 64. In the next level from 64 to it will go to 256. So, this is the way you can systematically build up the clock tree. Now, suppose after 4 or 5 iterations you will have sufficient number of clock points which will be distributed regularly throughout the chip, because if you go on carrying out this iteration, these points will be slowly and uniformly getting distributed all throughout the chips. So, in all parts of the chip you will be getting some clock pin which is very nearby, right. Now in terms of the buffer, well, if you have a clock tree, you can introduce a buffer at the center. So you can do it uniformly. So you can put buffers in the centers of these edges. So insertion of buffer is also very regular here, once you have the layout of the clock tree. So this mechanism, well, this I have said, the distance is same. This can be generalized to have n points where you can have the clock, where n is some power of 4, because at every step from each point you are generating 4 new points. So it will be some power of 4. This m is the number of iterations you are going through. Depending on the number of iterations, the number of clock points will be 4 to the power that. Now, there is one issue in this method. Well, this method is apparently very regular, it has a very nice geometrical property, so that all throughout the chip you can get the clock pins. But in a practical design, do you need the clock pins uniformly distributed throughout the chips? Usually no. You have such a requirement for FPGAs or gate arrays, where the cells are pre-placed and they are pre-placed in very uniform locations, and each cell in the FPGA typically also has a clock input. So you need to distribute the clock to uniform points throughout the chip. So for those kind of environment, this H-tree method can prove beneficial. But for general standard cell or custom cell based designs, there this H-tree may not prove too much beneficial, because from the final destination you will find that the point you will have to draw the clock, that can be at some distance. So you may have to draw a line from there. Moreover, some of the points may be wasted, you do not need them. Okay.
So how does it ensure minimum delay routing?
Minimum delay? Well, you see, with respect to this is the source of the clock, these are the destinations. The way we have calculated the destination, these are based on rectilinear distances, Manhattan distances. So if we assume that the clock routing net will be consisting of only horizontal and vertical segments of the lines, this is the shortest distance, because these are all Manhattan distances. Say from this to the farthest pin, you cannot have any net which is smaller than this. Coming back, you could have a shorter one, but in order to have that equal length limitation, we have laid it out like this. Okay. Now, normally since the clock net is laid out on a separate layer, as I had said, so there need not be a hard and fast restriction that the lines should be horizontal and vertical always. So there is a variation of the H-tree based algorithm. This is called X-tree. This is very similar in concept. Here, instead of that H kind of a structure growing recursively, we have an X-shaped structure. Now, X-shaped structure means the lines can run at an angle of 45 degrees. So any line running 45 degrees will join 2 points which will be smaller than the Manhattan distance. So typically in this kind of an X-tree based algorithm, the delay will be smaller. Delay means the delay of the clock signal from the source to destination. Now in this sense, this can prove to be better than H. I have an example, I will show the show diagram. This can be better than H-tree in terms of delays. But one problem arises, because in the H-tree, because of horizontal and vertical segments, the line layout are very uniform and some minimum spacing can be ensured. But in X-shaped wires, if you go on recursively generating that kind of a structure, you will see that in some corners, some of the wires may come very close together, and in some other corner wires are not that much close together. So the capacitive coupling of the wires may not be uniform all throughout. This is one drawback of this X-shaped. And the X-tree based algorithm is also suitable for distributing the clock signals regularly. So it is applicable to structures like FPGAs or gate arrays, not applicable in general ASICs. Okay, so let us look at an X tree structure. Well, I have shown you this structure at the end of iteration 2. So, the first iteration, this was the X which was constructed. This is an X which connects these 4 points, and the clock source was the center of the X. So, in the next level of iteration, from this center you generate another X, another X, another X, another X. This will go on extending. Now, as I said that as you do this, there are some pairs of wire, like here these two lines are so close together, but the other lines are not close together. So, there will be unequal coupling between these pairs of lines. So, the delays of the different segments may still be slightly different. Okay. So, this H and X are very similar in terms of the layout, but only the wires here are running in a non-rectilinear fashion. They are running at angles of 45 and 135 degrees. Okay. Fine.
Here also we have a single layer for the clock.
Single layer for the clock, yes. Normally, all the clock routing algorithms, they route the clock on a single layer. But now let us look at a scheme which is based on a non-regular clock distribution requirement. Well, you have an ASIC, it can be a standard cell, it can be a custom design, that the clock net points may be distributed across the chip. There, one method which you can use is called the method of means and medians. This is called MMM in short. Now, in concept, it follows a strategy very similar to the H tree algorithm, but here the issue is that the arms of the H may not all be parallel. Well, you can, depending on the requirement of the destination point, you can have an H which looks like this or like this. So, the shapes of the H's are not regular. So, you are making these adjustments depending on which are the points you need to distribute the clock net to. In concept, this is similar to the H tree algorithm, because your whole interconnection network will look like an H tree network, but with the lines or zigzag kind of lines. These will not be rectilinear lines again. Now, the way it proceeds is that we recursively partition a circuit into two equal parts. Now, this equal parts is typically in terms of size, but in some cases you can also partition them in terms of the number of clock points. These equal parts which I am saying, these equal parts may also be in terms of the number of clock points you need to connect to, right. Now, in each of the partitions you compute the center of mass. Suppose in one partition you have a requirement that you have a clock pin here, clock pin here, clock pin here. Given points, there are well known algorithms to compute the center of mass. Well, here the center of mass will be somewhere here. You treat this as the center of this partition and you connect the center of mass of the whole circuit to the center of mass of the partition subcircuits, and this you go on doing recursively. This actually I have an example to show you, but first let us look at slightly more into the detail of this, that how we do this partitioning. Yes, yes, they are all identical. The masses of the individual points are same. Yes, they do not have weight, but in some cases you may choose to assign weights to the points if some particular point is more important than the others. But normally they are all equal, because for the clock net in particular they are treated all equal. Fine. So, the partitioning is normally done using a simple algorithm like this. This Lx is a list It is a list of clock points which are sorted according to that x coordinate, from left to right you sort them. Px is the median in Lx, that means that is the middle point. They are, the number of clock points to the left and right are equal. So, at Px you can do the partition. So, you have the layout, the clock points are all distributed, you find Px and you decide to make a partition like this. So, all points to the left of Px you call them PL, left, all points to the right you call them PR, right. Yes.
So these clock points mean like for the function units?
Yes, you have the placement done, you have on each block some pins where you have to feed the clock, those are the points. Fine. So, we do a vertical partitioning like this, then in the next step we do a horizontal partitioning. Now, horizontal partitioning may not be uniform all throughout, it may be like this also. You partition this portion, partition also this portion. I have an example, I will show you. So, there again I call it PB and PT, bottom and top. In this way you go on recursively doing it, once vertically, once horizontally. So, this process is repeated iteratively till the, well, basic block has only 2 points which you can connect directly. So, I have an example to show you. Suppose you have an example like this. This is the original problem where you have the clock points distributed. So, you find out a cut point based on the median, so that the number of clock points are equally distributed to the left and right. Then you partition them in the horizontal line. Now, this was the vertical partition. Now, for the left partition the median will lie here, for the right partition the median will lie here, they may not be in the same place. You continue doing this. Now, with a vertical partition. So, now we have a situation where in each partition the number of clock pins are 2. So, you can directly connect them in each of the partition with a line. Now, the center of mass that I was talking about, now you can backtrack from this one and go on computing the center of mass and complete the tree. See, now we have these individual line segments. Now, with respect to each line segment, the center of the line segment will be the center of mass. So, the center of each line segment will be the corresponding center of masses. Now, the last partition was by these vertical lines. So, you connect the center of mass of this to the center of mass of this, center of mass of this to the center of mass of this to this and this to this. In the next step, these lines using which you have connected, now in this sub circuit you again compute the center of the mass. That will, it can be shown that center of mass will lie on this connecting straight line somewhere on there. So, in the next step you connect them like this, like this. Huh? It will be on the center, yeah. It will be center. If means all are identical, it will be on the center of that line also. Similarly, these two will be connected like this. So, finally, you will be having a network which looks like this. Well, it is an H, but the H edges are all zigzag. So, in the H tree algorithm, the lines are constrained to be horizontal and vertical only, but here you can have any arbitrary angle. Clock skew will be there, but you are trying to minimize it. See, here you are not making an exact estimate and try to make it equal. You are trying to see that in all portions of the circuit, see, this each junction of this will be having a buffer. Okay, there will be a buffer inserted in each of these junctions. Now, if you do this, the clock skew will be less, not means 0. You are not trying to make it 0 here. There will be clock skew, unlike the H tree algorithm where the path lengths are equal, but here the path lengths are not equal, but you are trying to make an uniform distribution all throughout the chip, means how we can lay out the clock. crosstalk is different, yes, that is there, but one thing you can ensure that say from the middle point of this line, the distance to each of these will be approximately equal. Since you are taking the median at each step, means you are taking the center of mass at each step and you are connecting like that. See, exactly equal you can never do, that is an ideal scenario, yeah. But one thing people have talked about, and in fact they do it for very high performance circuit design, this is something called zero skew clock routing. See, buffers in the net, you can put them at the junctions of, see in the H tree algorithm what you are doing, if your H was like this, then you are putting the buffers at each of the junctions, say one here, one here, one here, one here, and finally one in the middle here.
We are using separate layer for this clock routing. So on that layer itself we are not putting the buffers. Buffers should be placed on.
Buffers can be laid out on a single layer layout of buffers are available. Okay, that is one thing I did not mention. Single layer layout of buffers are available. I mean the interconnection, that means the input and output, yeah. But they will have to go through the polysilicon diffusion layer because they are active components. See, but here the delays are more important in the buffer. The delay should all be equal. The unequal delays we are eliminating.
Basically, this is a more realistic algorithm.
More realistic algorithm, true, true. But in some very high performance designs, people talk about zero skew clock routing. See, in order to estimate the exact delay, you have to go for a very accurate model for the interconnecting lines and estimate the exact delay of that. I mean, one popular delay model is the Elmore delay model. So, in the zero skew clock routing, what it says is that you estimate the exact RC delays of the interconnecting lines by modeling them using the Elmore delay model. And well, you can use an extension of the previous algorithm. You are simply computing the center of the mass, but center of the mass computation will not do. You will have to calculate the delays of the individual lines, and based on that you will have to take the center. Some lines are in close proximity, some lines are in not. So, you have to take everything into account and you will have to find the zero skew clock routing point at each level of the iteration and interconnect them stepwise. So, it is a complex process, it requires a lot of computation. Okay, so, but this is what people do for very high performance designs. Okay, fine. So, we quickly look at the issue of the power and ground routing as well, because power and ground routing is also important. They have to carry quite a high current drive, and all the functional blocks in a typical circuit require power and ground connections typically. Okay, unless if there are basically some are pass transistor networks, they do not need power, but most of the other blocks they need. Now, power and ground nets are again usually laid out on the metal layers of the chip, not necessarily on a single layer. It may be on a single layer, maybe on two layers also, but only on the metal layers due to their low impedance. So, here we shall be looking at some of the interconnection topologies. So, we will be basically looking at two things: construction of the interconnection topology, this is one issue, and after the topology is constructed, you will have to do another thing here. You will have to estimate the current that need to flow through the different segments of the tree and accordingly size the widths of the individual segments. So, the power and ground nets are one where the widths of the different net segments may vary depending on the total current carrying capacity. Now, for VDD and ground, obviously the requirement is that we will require two non-intersecting interconnecting trees. The trees will be non-interconnecting obviously, the widths of the trees will be variable depending on the total current carrying capacity at that point of the tree. Now, there are several approaches which have been proposed, we will be looking at a couple of them. First one is a very simple approach, this is suitable for standard cell based designs. Here we assume some kind of a grid structure. Several rows of horizontal wires for VDD and ground run on one metal layer, the vertical wires run on separate layer. So, I am showing you I am explaining this with the help of example, a diagram. Say this. This is the layout of a chip, these are the input output pads. I am assuming that on the left side of the chip there are several IO pads which are feeding VDD. Well, instead of a single VDD pin, you can have several, so that the drive is more. So, you have a net on the left side, this one, from here several rows are running like this, these are the VDD rows. Similarly, from the other side there is a ground net, there are several points again on the other side for ground, there is a vertical line like this, and from here you have several such ground line running. So, it is like a comb, from both sides a comb is coming, and if it is standard cell based design, for the cell rows which are laid out in between, you can uniformly get VDD and ground in all rows in uniform places. So, this is a very common kind of a layout for standard cell based designs, and between the horizontal and vertical connections you can have those via connection, not necessarily in one point, but in all points, in order to reduce the resistance. These are all unipotential nets, VDD and ground. So, there is one VDD lying here and there are number of VDD lines coming, and again in the next stage you can have vertical lines running down below, again another level of comp. Okay. So, this you can continue. So, in a standard cell design you may not need the second level, that depends on your requirement. Okay. And the second approach that we talk about, this is a more general approach where the clock and ground net may be required to be routed to arbitrary locations. This is called interdigitated trees. So, the idea is that VDD net and the ground net, say the VDD net you start routing from the left edge of the chip and the ground net you start from the right edge, and you start routing them. For example, this is your chip, you divide the chip into half, from this direction you start with VDD, from this direction you start with ground, right, and the way this VDD and ground nets are connected to the destination points, here they are done using a combination of lease and line search algorithms. See, if you start the VDD net from the left, this is the middle point. So, the rule of thumb says that for the VDD points on the left side of the chip, you use the line search algorithm, they will be done very fast, there are no other nets which are interfering. Similarly, for the ground net coming from here, you use the right half and you use the line search algorithm for routing them. But as these nets cross, the VDD net cross the right side, the ground nets cross the left side, there will be now lot of obstacles on the other net. So, now better use the lease algorithm. This is how it is done. And one typical example of an interdigitated tree layout is this. So, from one side you have the VDD net starting, from the other side you have the ground net starting. So, this is I am showing the final layout, but what I am saying that half of this was done using line search and half of this was done using lease. That is what is typically done, and the sizing and the width of the nets, this have to be computed separately using a power estimator tool, and you can just do this sizing separately. So, we have looked at the the issue of clock and VDD ground routing, that means what kind of routers are needed for this. Now, in our next class we will be continuing with this, and we will be looking at some other specialized routing techniques like the over the cell routing, one thing I mentioned earlier, and we would also be talking about layout compaction. So, after this layout, how we can do the compaction. Thank you.